Hi everyone, today I'll be discussing about my project Adaptive Algorithms for Detecting Community Structure in Dynamic Social Networks. This will be the main contents of my presentation. First I'll start with an introduction to community detection, and we'll see the differences between community detection and graph clustering. Then we'll see differences between the static methods and dynamic methods used for graph clustering or community detection. Then we'll look at some of the preliminaries, which are where we see about the different notations used for representing graphs. Then we'll look at the main algorithms proposed, which is the quick community adaptation. Then we'll look at the various simulations and results, followed by the conclusion of the project. Community detection. Community detection is basically gathering of the network vertices into groups such that the nodes in each group are densely connected within the group and sparsely outside. We group the entire nodes in the network into different groups, and it has many applications in social network problems and in routing of mobile ad hoc networks and in worm containments in cellular networks. The community detection and graph clustering both have a common objective, which is dividing the network into groups of nodes. But in the case of graph clustering, we give the number of clusters as an input to the algorithm. This, irrespective of the community structure, the algorithm divides the network into a specified number of clusters. This is very inefficient because initially, if we don't know the community structure, so the algorithm might end up dividing the community, might incorrectly dividing the network into different clusters. Thus, in community detection, the number of communities is unknown. Just based on the network structure, the algorithm decides the number of clusters, and it divides the entire network into different communities. There are many static and dynamic methods for community detection, but basically a dynamic network is a special network where the network properties keep changing over time. That is, the new nodes keep adding, and the new edges are formed, or maybe the edges might be removed and the nodes might be removed. Some of the examples of the dynamic networks are the communication networks or the social networks. For example, in the case of social networks, the new users keep joining social networks, and they keep joining different communities as the hobbies of the people keep changing, so they might be moving to different communities. Thus, the structure of the network is very dynamic as the network properties keep changing over time. So, to detect the communities in this kind of network, if we use static methods, which actually evaluate the community structure from the scratch for every change in network structure, we have like many disadvantages. That is, like for huge networks, they take large running times, and they might get trapped in some local optima. And even for small changes which are done, which are made in some local part of the network, actually the static algorithms construct the entire network from the scratch, and hence it is very inefficient, and as it consumes a large time. Whereas dynamic networks actually adapts the network's community from the previous known structures. That is, it uses the previous measurements to communicate the new network structure, and hence it is very efficient and less time consuming. These are some of the notations in the graph. In the case of static network, so a graph is represented by v comma e, where v represents a set of vertices and e represents a set of edges, and these are the other commonly used notations of the graph. And these are the other some of the other notations which are used for representing dynamic networks. The modularity is the objective function which we have considered for measuring the community structure, or the structure which has been prepared by the algorithm. Thus, higher the value of q, higher is the modularity, or higher is the community structure of the network. Coming to the algorithm, the main objective behind this algorithm is to devise an adaptive algorithm to efficiently detect and identify the network community structure at any point using the previously calculated structure. So thus we can measure the evolution of the network over time. So any changes to the network have been classified as can be classified as one of these four events. That is, adding of a new node, removing of any of the node, adding a new edge, or removing any of the edge. So before actually applying any of the algorithms for these events, first we should know the basic structure of the network. Thus, one of the static methods is used for measuring the basic community structure. So for my project, I have used Lowen method for static community detection. So The first algorithm is a new node. For this algorithm, we give input as the new node, which is has to be added to the network, and the current community structure, and the output of the algorithm has to be the new updated structure. So if the new node which is added doesn't have any adjacent edges, so the new community structure will be just the old community structure plus a singleton, which is the new node added. Thus the modularity doesn't change. But whereas if the node has some associate edges, then first we actually create a new community for you. Then we find all the vertices which are incident to you, and find out the communities of those vertices, and then to all those communities to which the U is connected, we calculate FC out, which is the force with which the community tries to bring the node U into it. So based on the forces of from all the adjacent communities, we find the maximum of these forces, and U will be joining that particular community. Thus the new community structure will be the old community structure minus the community containing U, and then the CU, like we remove the community which U is going to join, and add the new community with U added to that. So the node removal is a very is third algorithm, and it is actually very complicated, because when a node is removed, all its associated edges are also removed. Thus it might actually the network community, the network structure might remain the same, or it might be broken into pieces, or it might be the broken pieces might merge with other communities and form entirely new network community structure. Thus it has to be carefully all the cases have to be carefully considered. So in this case there we consider two main cases. That is, if the node which is being removed is of single degree, then there is no change to the community structure. But whereas if the node which is being removed is of highest degree, so in that case we use a click percolation method to find out the new community structure, where we place a 3-click at one of the neighbors and let the click percolate until no vertices in C are discovered. Then all the remaining singletons are other clicks. They when we see to which by adding them to which community increases the higher, maximizes the modularity, and they're added to the respective communities, and the community structure is updated. And the final algorithm is for edge removal. So edge removal, we give the edge which has to be removed and the previous community structure as an input to the algorithm, and here we consider 4 different cases. If the edge which is being removed is a single edge, that is, if it is not associated with any of the communities, then by removing that edge, the U and V become singletons, that is like communities with single elements, and thus the community, previously community structure is, we remove this U comma V, the edge containing U comma V, then we add the U comma V as a singletons. Whereas if in the second case, if either U or V is of a single degree, then we just remove the node, we just remove the edge containing U and V, and we update like either U or V as a singleton and update the community structure. If U and V belong to 2 different communities, then it doesn't affect the community structure, it just strengthens the community structure, so the community structure remains intact here. But whereas in the final case, if it is an intra-community link, so then it's very complicated, as this might if the community is very densely connected, then it doesn't affect the community structure. But whereas if it is loosely connected, then it would definitely might lead to like the splitting of the community into various networks. So in this case, we find all the maximum costly clicks within the community, and also we calculate the different singletons and determine like the best community for them, and thus update the community structure. This QCA to like for so this is the main algorithm where we give the initial community structure and the different events which are like any of the above mentioned 4 events. So initially, using any of the static methods, the community structure is calculated, and based on the network event, the corresponding algorithm is run to update to get the updated community structure. Thus, this method doesn't actually calculate the community structure from the scratch for any network change. It just uses the previously calculated network structure and just updates it. And thus, it is very efficient and consumes less time. So, coming to the simulation results, I have used 7 different network communities data which I've collected from the internet for measuring the for evaluating the performance of this algorithm. So due to unavailability of dynamic data, I have used the static data, but initially I have considered each node as a single cluster. So initially you can see the evolution of the network with the time frame. So initially all the nodes are considered as separate clusters. Then I kept on adding some of the edges. So as and when, as the number of edges are are added to the network, so the community structure becomes stronger, and hence the number of communities are decreased. This this is the first example where I have collected data from the Wikipedia, which is from the Wikipedia voting. So there was some voting conducted in the Wikipedia, and there were about 7,515 nodes, and the number about 0.1 million edges. So this is the first network. This is the second network which has been collected about from the collaboration network of Azev's high energy physics theory, and there it shows the evolution of the network structure, and it can be seen as the time progresses and as the number of edges are added, so the community structure becomes strong, the community structure improves, that is the modularity improves, and hence the number of communities are decreased. Initially as previously I have said, all the nodes are considered as single clusters, and as the time progresses, so the community structure is improved. The third network is the jazz network. So all the jazz musicians, so there is some data related to them. So it has 198 nodes and about 10,000 edges. So this shows the evolution of the community structure in this network. The fourth cluster community structure refers to the OC Links website. It is a social network related to the Orange County in California, and it has about 1899 nodes and about 40,000 edges. So this shows the evolution of the network with time. The third, the fifth community structure is the Marvel social network structure. So it shows it has 1500 edges and about 5800 nodes, and here we can see the evolution of the community structure over time in this network. And the final network which is considered is a school network, where we can see that it has 236 edges and 236 nodes and 11,000 edges, and as the face-to-face communications between the students is increasing, so the community structure keeps on decreasing. The community structure keeps on improving, that is the number of communities keeps on decreasing. So the data has been collected over 2 days. So this shows the community structure on day 1, and here we can see the community structure on day 2. Here in case we have 238 nodes and about 11,000 edges. Okay, now we will see at some of the simulations. So the network data which was collected was in the form of different formats. So to get the mat file, so a Python script has been written to parse through the scripts and get the text get the data from these scripts. And this is one of the MATLAB files which to parse through the text files and generate the mat files. And this is the main code where I have written about the algorithms to evaluate the network community structure. I'm running this for the Jazz network, which is the smallest of all the networks, because the community detection takes a huge amount of time over large networks. Some of them they even run for about 45 minutes. So now here we can see the evolution of the network in the case of Jazz networks.